This video represents a further continuation of our discussion of valence bond theory as applied to the formation of pi bonds. As an example of a compound that has a pi bond, we want to consider something like ethylene. Ethylene has a formula of C2H4 and has the Lewis dot structure you see here. In order to complete the octet for the carbon atoms, we needed a double bond between the two carbon atoms. In this particular case, then, we're going to focus in on one of the carbons at a time here. You'll notice that there are 3 electron regions around that carbon, so we will then need an sp2 type hybrid orbital. The angles for the HCH are approximately 120 degrees, and so as you can see from the energy diagram for an individual carbon atom, we would then need to promote an s electron up into the 2p orbital. This then produces our sp2 hybrid type orbitals, and then also leaves behind the one electron in a purely 2p type orbital. So when we go about then forming our bonds, we are going to have the sp2 type hybrid orbitals form our sigma bonds between the carbon and the hydrogen atoms, but also then forming a carbon-carbon bond by the overlap of one of the sp hybrids on each of the carbons, so that we end up with a sigma bond between the two carbons. In addition to that, then, we also have to account for the fact that we have that one remaining electron in the 2p orbital. In this particular case, that remaining p orbital, it has 2 lobes that are above and below the planes associated with the other atoms, and so when there is an overlap between those 2 p orbitals, we can get constructive interference, and so in this case then the formation of the so-called pi bond. As a further example of the formation of pi bonds, we want to consider a molecule like acetylene, which happens to have a triple bond between the 2 carbon atoms. And so in this case we have our Lewis dot structure as shown here. In this case, again, we're going to focus in on a single carbon atom, and we see that in this case, if we then take our energy diagram, we are going to need to form sp hybrid orbitals so that we end up with a linear arrangement, 180 degrees between the hydrogen, the carbon, and the other carbon. So in this case, if we go ahead and form our hybrid orbitals, we end up with a situation where there are 2 sp hybrids on each of the carbon atoms. That leaves behind 2 electrons in the purely 2p type orbitals, which are a little bit higher than the hybrid orbitals. And at this point, we can go ahead and make our sigma bonds. So there are 2 different kinds of sigma bonds that we're going to form. Each of the carbons is going to form a bond to a hydrogen, and so that will then pair up the hydrogen's electron with the one of the sp on each of the carbons. And then in addition to that, we can form our carbon-carbon bond. Alright, so both of those being sigma type bond because there's a direct overlap coinciding with the axis of the bonds between the atoms. And then finally, we need to consider the possibility of the remaining p orbitals on each of the carbons having their sideways overlap, and there are 2 possible combinations for that. So hence the additional 2 bonds in the Lewis dot structure for a total of the triple bond. So we use those to form our pi bonds for the two carbon atoms. So this slide summarizes what we've done here in terms of valence bond theory. And so basically it comes down to if a molecule has a single bond between two atoms, that bond must be a direct overlap of the hybrid orbitals on the two different atoms, and we refer to this as a sigma bond. If we have a double bond between two atoms, the first of the two bonds will be a direct overlap and referred to as a sigma bond, but the second bond in the double bond will be a sideways overlap or a pi bond. If a molecule contains a triple bond, the triple bond will consist of one sigma bond and two combinations of sideways overlapping pi bonds. There are physical consequences to the nature of the bonding in various molecules in terms of the ability of groups of atoms to rotate around bonds. It turns out that since a single bond has only a sigma type bonding orbital, which is a direct overlap between two atoms and is completely symmetrical with respect to the axis of the bond, that these groups of atoms can rotate around single bonds freely or with relatively low energy barriers. And so typically these rotations are occurring quite rapidly at room temperature. So we end up getting a twisting of the structure, and we come up with quite a number of possible orientations of all the atoms in a molecule, as you see here. Alternatively, if there are double bonds between the two central atoms, as we see here in what we call 1,2-dichloroethene, in that case, the rotation around a double bond is not completely symmetric with respect to the orientation of all the groups. And in this case, there is restricted rotation around the double bond. And so it turns out that there are two possible orientations of the two chlorine atoms, and they do not readily interconvert between each other as they would if it was a single bond. So in this particular case then, we have to account for this in terms of how we name this. We add the additional information of the so-called cis and trans. The cis situation is where the two chlorine atoms are in close proximity to one another. Trans is when they are on opposite sides.